Good morning, ladies and gentlemen. Please raise your hand if you did not get a red mark for today, the 8th. Okay, and so I want you to tell me then what derivative tells us about increasing versus decreasing behavior, the first derivative or the second derivative? Megan?
The first derivative.
The first derivative, thank you. And so we can determine where my function is increasing versus decreasing by analyzing the first derivative, y prime, and performing a sign diagrams chart. So let's go ahead and get my first derivative. Go ahead and tell the class y prime term by term when I call on you. So what would y prime be, given that y is this cubic polynomial? Maggie?
3x squared minus 6x minus.
Raise your hand if you have the same first derivative as Maggie, please. Awesome, thanks, hands down. We know that a function, right, a function has critical points wherever its first derivative y prime is 0 or undefined. And as I look at this expression for y prime, a nice, well-behaved quadratic polynomial, I know there's no values of x for which y prime is undefined. However, there certainly may be values of x for which y prime equals 0. So I'll go ahead and set y prime equal to 0 and solve to determine any critical values of my original function. They're so named because those are the only places where y could change direction. That is, switch from increasing to decreasing or vice versa. So here we go. Stop. Think. GCF. I'm going to go ahead and pull out a 3 from each term. I think that's going to make an easier factorization here. So I've got x squared minus 2x minus 3. And I'll continue factoring that black trinomial until the product of two binomials. This looks like an undue FOIL problem, so I'll keep that 3 just chilling. But I'll break up that x squared minus 2x minus 3, and we'll factor that. It looks to me like our firsts are x and x. Looks like our lasts are 1 and 3. And it looks like my signs, in order to create an outer product and an inner product, sum to give me that negative 2x, we're going to have the larger with the negative, 3 and the positive 1, so that my opposite signs multiply to create a negative last term in my black trinomial. All right, so now that I have this factored, I'm going to go ahead and set each individual factor equal to 0 and solve separately. It looks like we've got critical values at x equals negative 1, because that would make my y prime equal 0. X equals positive 3, because that would make my y prime equal 0. And this first factor 3, is not going to equal 0 ever. And so it looks like I have two critical values. Please raise your hand if you determine the y's critical values at the same places. X equals negative 1 and x equals positive 3. You got those? Great. So now it's time to perform our sign analysis on y prime. So we'll go ahead and make a y prime number line. We're going to make a y prime number line. You must label this. In fact, you'll get points just for labeling your number lines on the Unit 8 test. So we'll label this our y prime number line. On it, we'll put our critical values. Then we determine x equals negative 1 and x equals positive 3. And then we'll perform our sign test using any expression for y prime. For me, it's easiest to determine the overall sign of y prime using the fully factored form. So I'm going to go ahead and go in this blue fully factored form. I'm going to choose a convenient x value in each subinterval. So tell the class the convenient x value to the left of negative 1. Michael? Negative 2, I'm down, so I'll plug that into my fully factored form for x and see what sign is produced for y prime. So negative 2 in for x. Negative 2 minus 1 is negative. Negative 2 minus 3 is negative. Negative times negative overall is positive. That 3 out front is always positive, so I'm not including that really as part of my analysis, but that's a positive 3. All right, convenient x value in my next subinterval. Emily? 0, I'm down, so I'll plug in 0 for x and get positive times negative. Overall, an odd number of negatives results in a negative sign for y prime during that subinterval. And lastly, a convenient value on the far right. Courtney?
4.
4, great. Let's plug in 4. I get positive times positive times positive. Overall is positive. So I've completed my sign analysis from y prime, and I now can see the intervals of increasing versus decreasing behavior on y based on the signs of y prime. I know y is increasing from negative infinity up until negative 1. A horizontal tangent at x equals negative 1 because y prime equals 0. Decreasing behavior for y on the subinterval x equals negative 1 to 3 because y prime is negative, and then increasing behavior for y after x equals 3 because y prime is positive. So depending upon the question, right, we would answer that and provide justifications based on our analysis. Recall, it's not enough on the AP calculus exam free response portion to simply use a sign chart, right, as your justification. You must refer to that sign chart and provide a justification using calculus. And so that's typically a derivative or one or more of the derivatives. And so we know y is increasing. We'll go ahead and write that, even though the question didn't ask specifically. I'll just abbreviate y increasing on negative infinity to 1 union 3 to infinity, and my justification would be because y prime is positive on those intervals. Similarly, y is decreasing on the subinterval negative 1 to 3 because y prime is negative. Awesome. So while we have completed our analysis for increasing versus decreasing behavior, we still need to consider the concavity. So go ahead and tell the class what derivative tells us about the concavity of y. I'm going to clone this page and clear the ink. So we have one more to work with here. So what derivative tells me about the concavity then? Marissa?
The second.
Second derivative, thanks, and so I'm just going to import our y prime. Maggie already told us 3x squared minus 6x minus 9. Go ahead and tell the class y double prime when I call it. So what my expression for y double prime be? Joel?
6x minus 6.
Awesome, thank you again. A nice, well-behaved linear function, no values for x, for which y double prime is undefined, but I still must consider when y double prime equals 0. Again, that would give me x coordinates of possible points of inflection, not necessarily points of inflection. I'd still have to complete a sign analysis on y double prime to determine, but it would give me possible points of inflection x values. So here we go, set equal to 0 and solve. Love factoring, factoring's our friend. It looks to me like inside x minus 1. So I've got possible points of inflection at x coordinate x equals 1. So possible points of inflection at x equals 1. And I don't know if that's going to contribute to a point of inflection until I perform my sign analysis. So here we go. We'll label our y double prime number line. On it, we'll start critical values. Well, I won't say critical values. They're not critical values. Remember, y prime equaling 0, y prime being undefined gives critical values of y. These are more of possible points of inflection x size. There's a single x coordinate 1, and we'll do our sign test. So here we go. Convenient x value to the left of x equals 1. Grace? 0. We'll plug that into any expression for y double prime. If I plug it into my fully factored form, it's easy to see this is positive times negative overall is negative. So I've got negative values of y prime on the interval negative infinity up until 1, and a convenient x value to the right, Riley E. 2, so I'll plug in 2, and I get 6 times a positive is positive. And so it looks like concave up behavior for y, right, to the right of x equals 1. So here we go. Y is concave down on negative infinity up until 1. Because, and you must put the because part if this is free response portion of the AP exam, because y double prime is negative. Furthermore, y is concave up on 1 to infinity because y double prime is positive on that interval. Awesome. Okay, so raise your hand if you got all the way to your concavity descriptions. So we got all the way to the concavity descriptions? Good, thanks, and now we're ready to put it all together. So let's see if we can't use our analysis of y prime and y double prime to qualitatively sketch a graph of y, my original function, without the use of a grapher, and then we'll check. So what do we need? Well, we still need an xy chart. So we'll go ahead and get the xy values. So I'll go ahead and choose any of my critical point x values, any of my point of inflection x values, and then I'll probably pick maybe a value on either side to try and flesh out what this looks like. So let's see, we need x equals -1, x equals 3, x equals +1, and 0 is usually easy to evaluate, so let's see if we can include those. So we've got -1, 0, 1, 3, and then maybe we'll see about -2 and +4 depending on how big this gets. So here we go. Negative 1 into my original produces negative 1. Minus 3 is negative 4. Plus 9 is 5. Plus 2 is 7. Raise your hand if you got negative 1, 7. Anybody get that far? So I did okay in my head. Great. Let's try 0. Oh, I got that one. 0, 2. Yay! That's my favorite one. And 1. So we'll do 1 minus 3 is negative 2. Minus 9 is negative 11. Plus 2 is negative 9. Raise your hand if you had 1, negative 9. Did you get that? That's right. Good. And lastly, let's do 3. So 3 into my original. 3 cubed is 27. Minus 3 times 9 is 27 is 0. Minus 9 is negative 27. Plus 2 is negative 25. So I'm getting 3 comma negative 25. Raise your hand if you also got that. Anybody else get that? Some confirmation, good? All right, so let's see if we can't make a graph here qualitatively. And I didn't even add any outside of bounds here. We certainly could do that. I saw we were getting a little bit bigger with our numbers here, though, so we'll see what happens. So we want to label these features. It looks like my 7 is the y-coordinate of a local maximum, because y prime switched from increasing to decreasing. So let's label that on our chart. So this is a local maximum. We saw that at x equals 3, y has a local minimum because y prime changed from negative to positive at x equals 3. So we'll label the y-coordinate as such. Bless you. Negative 9 must be a local minimum. And we see the, nope, wasn't it 3? Yeah. So negative 25. There, that'll fit. And we saw that at x equals 1, y double prime changed sign, so this must be a point of inflection. So 1 comma negative 9 must be an inflection point. And I'll show that with a little x on our graph. Okay, so what do we need? Negative 25 is my local minimum, and then it's back increasing again. Yikes. And so I'm going to go ahead and make a scale that'll just be qualitative in nature. So it looks like I need to get down to negative 25. So maybe I want to go 5, 10, 15, 20, 25. 5, 10, 15, 20, 25. Okay, and my x value scale, though, is going to be somewhat zoomed in. So it looks like I only have from negative 1, 0, 1, 3. So maybe I go negative 5 to 5. Will be okay, negative 5 to 5. All right. Whew. Moment of truth. Here we go. We've got a local maximum at negative 1 comma 7. Here it comes. Negative 1 comma 7 is right about there. We've got a y-intercept at 0 comma 2. That's right about here. We've got a point of inflection at 1 comma negative 9. That's right about here. I'm going to mark that with a little X there. That's letting me know and you know that that's where we intend the curvature to change. So if you, again, that's not a College Board free response type thing. It's just so that I can see where you're intending the function to change curvature. And if you do that on your test or quiz, it'll make it easier for me to see as well. Then we've got a local minimum for my function at 3 comma negative 25. So that would be 1, 2, 3 comma negative 25 is right here. Tomatoes? And we've got a horizontal tangent because y prime equals 0 to x equals negative 1. So at x equals negative 1, that's here. We had a horizontal tangent because y prime equals 0 at x equals 3, so we can flesh that in. We had change of curvature at my point of inflection at x equals positive 1. Before it, we were concave down. After, we're concave up. So concave down before and concave up after. Well, it's not the prettiest cubic function I've ever done. I'm getting some reminders of Salvador Dali's melted clocks. But I tried, so let's go ahead and see what we can do. So in my original, I'm going to put x cubed I kind of like the math 3 shortcut, that's pretty sweet. Minus 3x squared minus 9x plus 2. I'll go ahead and make sure that we have the same window so we can compare. We went negative 5 to 5 for x's. For y's, we went negative 25, so I'll go negative 30 to 30. Oh boy. Moment of truth. Pinch of salt. And coming up. On. And down. Ooh, and up. Well, that's pretty good. Keeping in mind that we could still, right, utilize our pre-calculus techniques for finding zeros in a function and all that business. We wanted to get more detailed, but again, we were just after our qualitative stuff, our extrema, our local extrema, and our intervals up on cap. Awesome. Hey, that's pretty good. And it's PDF for full show, Kyle. All right. What questions do you guys have about our graphical analysis for Bellwork? That, in a nutshell, is what we did last class period, and today we're going to continue our discussion to include not just local extrema, but absolute extrema. We're also going to take a look at the second derivative test, and we're going to do that actually before our homework collection, because I'd like to go ahead and use that in our graph that we just created, since we're all familiar with it now, whether we were here or not last time. So take a look at the second derivative test. This is not on your note sheet. I added it last class after deleting it from our graphing slides, kind of to do sort of one thing at a time. So we need to add this somewhere, okay? So the second derivative test is a means for determining local extrema, right, based on the interplay between y prime and y double prime. Again, the first and second derivative. This is a way it allows us to do it if it's difficult developing a sign chart for y prime, or as a means of verifying, right, what we think to be going on. Or if we've got problems with our expression and just have numerical data, I mean, we don't have a symbolic representation for y prime or y double prime. Okay, so if y prime is 0 and y double prime is positive, then we can determine a type of local extreme that y has. Let's consider just the first part in red. If y prime equals 0, right, what does that indicate about my y function? Well, I don't know that we have a local max or a local min, but I know one thing for sure. Y prime equals 0, what must y have at that point? Brandon?
Critical point?
Yes, it has a critical point, right? But because y prime equals 0, right, because y prime equals 0, then we know the slope of y is 0. And so what feature would that be?
That would be a horizontal tangent.
Absolutely. And so we know we have a horizontal tangent on y. And so y would have a horizontal tangent. And let's focus on the y double prime being positive portion. If y double prime is positive, what does that tell me about my original function y? Kyle?
Concave up.
Concave up. And so if we consider putting these two things together, if y prime is 0, that's horizontal tangent, and y double prime is positive, that's concave up, what feature must y have at x equals c, right? What feature must we have then? Hayden? What? Yeah, but it could be a cubic function, it could be a quartic function, it could be an exponential function, right? Or combination with algebraic. But no matter what, we have what feature? A local max or a local min, if we put those two together? A local minimum, right? We'd have a local minimum. So horizontal tangent and concave up allows us enough information to determine we've got a local minimum. So y would have a local minimum. Awesome. The second piece, then we get the scheme. We know that y prime equaling 0 means y has a horizontal tangent. Y double prime being negative then would be concave down behavior. So if we put that together, we'd have this type of situation, horizontal tangent. And so we must be experiencing what type of extreme? Well, then y has a local maximum. So once again, if y prime equals 0 and y double prime is negative, then we have no choice but for y to have a local maximum. let's go ahead and now take a look back at the cubic function we just graphed. So once again, if y prime equals 0 and y double prime is positive, then we know we're dealing with a concave up bowl shape, therefore we must have a local minimum, and the reverse for y double prime negative. So let's go ahead and see. At x equals -1, we had a y prime equals 0. However, y double prime was negative. So if we put those two things together, we could have seen, without making a graph, that y has a local maximum there. Again, concave down, but horizontal tangent must be local maximum. My other place where y prime equals 0, right? My other place where y prime equals 0 was at x equals 3. At x equals 3, we had a horizontal tangent. However, my y double prime sign chart indicated concave up behavior on y. Therefore, the only way to have horizontal tangent and concave up behavior is if we had a, you guessed it, a local minimum, and we see that visually as well. And so the second derivative test is just another tool in your bag, right? Another tool in your bag. Particularly if you don't have an algebraic expression, we can't do our sign test the same way. We're just given maybe information in a table, right? We can compare y prime equaling 0 and determine if, and look and see if y double prime were positive or negative. That would be enough to determine then local extrema. So that's another tool in your bag, so to speak. What questions do you guys have about our Bellwork discussion today? Thank you for adding the second derivative test to your note sheet. All right, let's go ahead and take care of our derivative review and our OTL sheet along with our bookwork. And so we got the stapler, and I'm going to pause the recording while we get this in order. Okay, ladies and gentlemen. So recall that a function's derivative tells us all about its behavior. By behavior, we're talking about increasing versus decreasing behavior and its concavity, right? The curvature of the graph. And so when y is increasing, what's true about y prime? Annika? Awesome. When y is decreasing, what's true about y prime? Riley Freeman? Negative, good. Horizontal tangent on y means that y prime is what? Michael?
0.
Is correct. And if y has a critical value, then we've got two different options. And so what are my two different options? For y to have a critical value, we've got two different options. Sophia?
0.
Yeah, y prime could be 0 or undefined, and we must consider both cases, right, when considering y's changing behavior. Awesome. Similarly, y double prime, right, y double prime tells us about the concavity. So if y is concave up, which resembles a portion of a right side up bowl shape, what's true about y double prime? Grace?
Positive.
Good. If y is concave down, what's true about y double prime? Marissa?
Negative.
Negative, thank you. And we have a possible point of inflection at x values where what's true about y double prime? Heavy?
0.
0 or?
Undefined.
Or undefined. Beautiful. And so remember, we could have a point of inflection where y double prime is 0 or undefined. We'll include those possible point of inflection x values in our sign analysis when we construct the y double prime number line. All right. We'll extend those relationships to y prime and y double prime. We've already done that. But first, let's go ahead and take a look at finding some absolute extrema. Up until now, with day 2, right, and day 2B's Bellwork, we've gone ahead and found local extremes, right? We found local extremes by using a y prime sign chart. In order to find absolute extrema, if our sole goal is to find absolute extrema, not necessarily construct a graph on our own, then we can do so without having to go through a y prime sign chart. We can do so by comparing the y coordinates at each of my critical values, since we know those are the only places where y could change direction. So those would be the only places where we could have local extremes, with the y coordinates of my endpoints on my specified interval. Whatever's the highest y value attained at between the critical point x coordinates / y coordinates and the endpoint values, that's going to be my absolute maximum. Whatever the least y value attained between my local extremes and my endpoints is going to be the absolute extrema. So we can do so and save time without having to do a y prime number line in the sign analysis. And so that's a good time save. If our only question is then to find the absolute extrema on the interval negative pi to pi, notice the specified interval, we can simply find our critical values, find our endpoint values, put them on an XY chart, and compare my y coordinates and answer the original question. Okay, so that would be a time saver. Let's go ahead and do this one together then. we still need y prime, in this case f prime, right? Because we need my critical points, and those come, as we just saw, from when y prime is 0 or undefined. So let's go ahead and get an expression for y prime. So here we go. If I were to differentiate f, I get to use a couple different rules here. It looks like f prime, my expression for f prime, would be the derivative of cosine of x. Well, we know cosine differentiates to the opposite of sine of x, minus, and now we get to use power rule, because overall cosine squared x is a power function. Cosine of x is the base, and the current exponent is 2. So let's go ahead and do a power rule for that. That's like current exponent is 2 times the base raised to 1 less is the first times the derivative of the base. The base in this power function was cosine of x. The derivative of the base is opposite sine of x. So it looks like my f prime expression can be simplified a little bit here. I'm getting negative sine of x. Negative times a negative overall is a positive 2 sine x cosine x. Is that what you guys are getting? So it looks to me like we get f prime is given by negative sine of x plus 2 sine x cosine of x. All right. Now I'll go ahead and get my critical points. Recall that critical points, right, come from when y prime is 0 or undefined. As I consider my expression for y prime, are there any values of x on my specified interval for which y prime, or f prime in this case, is undefined? No, sine of x is smooth and well-behaved for all x values, so is cosine of x, and so their product should be smooth and well-behaved for all x values. So certainly on this restricted domain, we're good to go. So there's no critical points that result from f prime being undefined. Are there any values of x for which y prime is equal to 0? Well, I don't know. Let's see. So we'll go ahead and set this equal to 0 and solve and determine any x values of critical points. So here we go. Negative sine x plus 2 sine x cosine x set equal to 0. I think factoring is going to be our tool here, even though we're dealing with trigonometric functions. It sure helped when we were doing our Bellwork with the polynomial. Let's do the same thing. So we're going to solve this trigonometric equation. I'm going to go ahead and factor out a GCF that looks like sine of x. Is sine of x the greatest common factor? So I'll factor out a sine of x from each term. And that would leave me with, inside the parentheses, I have negative 1 plus 2 cosine of x. Is that right? And I can solve the fully factored equation set equal to 0 by utilizing the zero product property. We'll go ahead and set each individual factor equal to 0 and solve separately. So my first situation would result from sine of x equaling 0. I'll consider when that happens on my specified interval in just a minute. My second situation would result from negative 1 plus 2 cosine of x equaling 0 on that specified interval. So let's see if we can generate any critical values here. Does sine of x ever equal 0 on the specified interval negative pi to pi? Well, let's get unit circle now. So negative pi is here. Spin around to positive pi. Was sine of x ever equal 0? Yes, sine of x is equal 0 at my endpoints, right? At my endpoints and at x equals, bless you, 0 and at pi again. And so it looks to me like we've got 3 critical values that are on my thing, but 2 of them are already endpoints. And so it looks like I've got CBs at x equals negative pi, x equals 0, x equals positive pi. Consider the next equation, negative 1 plus 2 cosine of x equaling 0. Does this ever happen on a specified interval? Well, I don't know. I'm going to do a little algebra. Does 2 cosine of x ever equal 1? That would happen if cosine of x was equal to, what, 1/2? 1/2? Does that ever happen on my specified interval? Well, let's see. So here we are at negative pi, and we're spinning. We want cosine to equal 1/2. Oh, so right here, right here we've got cosine of x equaling 1/2, the x squared equals 1/2. Then comes a 1, and then yet again we've got a positive 1/2 for cosine, and then back to pi. So it looks to me like this happens twice. When does cosine equal 1/2? Riley?
When x equals pi over 3.
pi over 3, right? My special 60 is when cosine is 1/2. And so it looks like pi over 3, and then the other one in my interval is negative pi over 3. And we begin to see why we began the year with the unit circle quiz, right? We've got to know our exact values without a calculator, right? We have to know those by heart. So it looks to me like, or be able to create them, right, without a calculator. So it looks like we've got critical values, more critical values, at x equals negative pi over 3 and positive pi over 3. Okay, so now that we've gone ahead and generated my critical values, I'm going to go ahead and scooch this over a little bit. And I'm going to make an XYT chart. And so my XYT chart, is going to simply be a way for comparing the y coordinates attained at my critical points with those attained at my endpoints so that I can pick out the greatest value. The greatest value from all those candidates is the absolute maximum. The least y coordinate from all those values is the absolute minimum. So let's find it. We'll go ahead and make an XYT chart. On that chart, what are we putting? We're putting the x coordinate of my critical values. So my x coordinate of the critical values are 0, negative pi over 3, positive pi over 3. My endpoint values are negative pi and pi. And we'll get the y coordinates for all of those. How did I get all of them? Did I miss any? So we want negative pi and pi, those are my endpoints. We want our critical values in between, included 0, negative pi over 3, and positive pi over 3. Let's evaluate my original function y. So where do I go? I go to my original f of x. Cosine of negative pi, right? Cosine of negative pi is negative 1. Is that right? Negative 1. Minus cosine of negative pi is still negative 1. Squared is positive 1. So I'm getting negative 1 minus 1. I'm getting negative 2. Is that what you guys are getting? Did I do that right? So cosine of negative pi is negative 1 minus negative 1 squared is 1. Negative 1 minus 1 is negative 2. I'm getting negative 2 twice. Right? Let's try at x equals pi, negative pi over 3. Let's see what f equals. And so we'll plug in negative pi over 3 in for x. Cosine of negative pi over 3 is 1/2. Minus cosine at negative pi over 3 is 1/2. Squared is 1/4. I'm getting 1/2 minus 1/4 equals 1/4. Is that what you guys are getting? Awesome. At x equals 0, cosine of 0 is 1. Minus cosine at 0 is 1. Squared is 1. 1 minus 1 equals 0. At x equals pi over 3, right? At x equals pi over 3, cosine is 1/2 minus cosine of pi over 3 is 1/2. Squared is 1/4. 1/2 minus 1/4. Again, I get 1/4. And lastly, cosine at pi is negative 1 minus cosine of pi is negative 1 squared is positive 1. Negative 1 minus 1 is negative 2 again. And so it looks to me like I've got y values of negative 2, 1/4, 0, 1/4, and negative 2. My absolute extrema question without a y prime sign analysis or chart is easily answered simply by comparing y coordinates. What's the greatest function value attained over my specified interval? 1/4. Yes, maximum? This is the absolute maximum. It's attained twice, but the absolute maximum is 1/4. So y has an absolute maximum of y equals 1/4. And it's attained at x equals negative pi over 3 and x equals positive pi over 3. But it asks for the absolute extrema, and that's a y coordinate. What's the absolute least function value attained over my specified interval? It looks like negative 2. Negative 2 is the least function value attained. That happens twice as well, and it happens at the endpoints. And so that's why we have to consider the endpoints as well. If we only did a y prime sign chart, we'd only be getting this local minimum. of y equals 0. And clearly there was a y coordinate that was less than that on my specified interval. So that's why I have to compare them with the y coordinates at the endpoints of my interval. So what can we say to finish this out? We'd say that we've got an absolute, y has an absolute minimum of y equals -2, and that occurs at x equals -pi and at x equals +pi. Now keep in mind that we've done this all algebraically and non-calculator. So now I want you to go ahead and flip the page, and let's see how we did it. So we said absolute max of 1/4. We said absolute min of -2, and by golly, that's -3, so -1, -2. So look, we got them. There's our y equals -2, -3.14, and at x equals pi over 3. This is pi over 2, so pi over 3 looks like y equals 1/4. So we did okay. Awesome. That was an interesting function. Cool. So moral of the story is, do we need to construct a y prime number line in order to find absolute extrema on a specified interval? No, we don't have to. We just need to find my critical points, still coming from y prime, but avoid the sign chart and simply make it a regular xy chart and evaluate the function at my critical values and my endpoints and compare it. That's a time saver. All right, let's go ahead and do one more tricky one. So we've graphed some polynomial functions for Bellwork. That was pretty easy. We went ahead and sketched some transcendental functions. Remember we did like y equals e to the x minus 1 and then closed exponent minus x. We did a radical function, an algebraic function. Let's go ahead and do one with some decimal exponents. So this could be a tricky analysis. Again, we don't have an intuitive understanding, at least I don't have an intuitive understanding of what these rational exponent functions look like, particularly when in combination. And so I might have an idea of what a direct power function looks like based on the exponent, but when we start combining things, I don't have a good idea of what this looks like. Let's use calculus to determine the function behavior of this function f of x. And so what do we need to do? Well, we need to know our intervals of increasing and decreasing, just like Bellwork. We need to know our intervals of concavity. And for this one, if we're going to go non-calculator, I'm thinking that maybe the zeros would be helpful, particularly since we can get those zeros just by factoring. And so I think that would be another thing that we could add from pre-calculus. So let's go ahead and make a sketch of this algebraically without a calculator. Are you guys up to the task? I'm up for it. Let's do it. Let's do it. Stay strong. So we get our f prime expression. We know that f of x is given by a sum or difference of individual power terms. I'll use the power rule singly term by term. So I know the derivative of my function f is given by exponent times the base raised to 1 less. What's 1 less than 1.2? 0.2. Minus 3 times exponent, current exponent is 0.2, so 0.2 times x to the 1 less than 0.2. What would be 1 less than 0.2? Negative 0.8. Okay. I'm going to go ahead and do a rewrite. So f prime of x equals 1.2x to the 0.2 minus 3 times 0.2 would be 0.6, is that right? X to the negative 0.8. And I know that my function f has critical values when f prime equals 0 or is undefined. So are there any values of x for which my function is undefined? Yes, I see that the second term is going to have a fraction. It will have a fraction, right, because x to the negative 0.8 is the same as 1 over x to the positive 0.8. I know that that would have an undefined value when x equals 0. So I've got a critical value at x equals 0 from this fractional expression. And I also need to see when it equals 0. So we'll go ahead and set it equal to 0 to solve to see when we have critical value. So here we go. I'm thinking factor first or fail. So we're going to go ahead and factor here. And so I'm going to factor out factor out a 0.6. I just want to factor out a 0.6. Yes? So we'll factor out a 0.6. And that would leave me with what? Well, leave me with x to the 0.2 minus, and then this would be 1 over x to the 0.8. Is that right?
2x.
2x? Yeah. For the first one? Wonderful. Thank you. Thank you. I'll go ahead and create a comment, yes?
Would we be able to take out x to the 0.2 and then multiply by x to the 4th or negative 4 for the next part?
Yes. Yes, absolutely. It's a question of when you want to do it. I was gonna make a common denominator here and then factor out an x. If we'd like to do it at the beginning, we certainly could take out an x to the 0.2. You want to do that? I think either way is fine. I'll do it in the beginning. Want to do it at the beginning? So let's do 0.6, and we're going to take out what? X to the 0.2? Yeah, 0.6, x to the 0.2. Okay? And then what would that leave us? In parentheses, oh. That would leave us with 2 minus 1 x to the, and now x to the 0.2 times what equals x to the 0.8? What's that? 1 over x. So x to the negative 1? I got better. A final rewrite, and I think we'll be good to go. Thanks, Evie. So common denominator, yes?
Can it be 4 over x to the 4th? Because it's to the negative 0.8, not 0.2.
But x to the 0.2
Divine powers.
times x to the negative 1 would be x to the 0.2 plus the negative 1 is negative 0.8, right? So we add exponents. Right, we add exponents when we multiply powers with like bases.
Yeah.
Okay? So all this is so we can say this is 2x minus 1 over x. Right? We did all that so we can say this. Okay, are there any values of x for which y prime is undefined? Yes.
Would that be x equals 0?
Yes. So y prime is undefined at x equals 0. Good. Are there any values of x for which y prime equals 0? Yes. That would be x equals 1/2. So let's go ahead and get our critical values then by considering our y prime expression. So we can do this. We've got critical values at x equals 0 and 1/2. Space, I got one more space, good. So let's go ahead and do our y prime, our f prime analysis. Here we go. On my number line for f prime, we'll put our x critical values, our 0 and 1/2. We'll choose a convenient x value on each subinterval, right? On each subinterval, we're going to choose a convenient x value. And so as I look to the left of 0, right, as I look to the left of 0, I'm thinking these are values that might be, want to do a negative 1? Can we try it? So this is 2/10 is a 1/5. So that's going to give me a negative 1 times the 1.2 is negative 1.2. Minus, and this is 1 over x to the 4/5. So that's going to give me a positive 1, but I had minus 0.06, right? I had negative 0.06. So times a positive 1. So I'm getting overall negative. Remember, we don't have to get exact value here. What we need to get is the sign. So I'm getting negative. You guys get negative? Can we try something in between 0 and 1/2? Can we do it? What's that?
Can we do a 4th?
We could do a 4th. It's just that we've got 5ths there. So what about a 32nd? Let's do a 32nd because I've got 5ths. Yeah, a 32nd? Oh, okay. Stay strong. Here we go. So this is, right? This is, oh, let's go to this part. So a 32nd, that's going to be positive, that's going to be positive. Let's just focus on my fully factored form. I should have done this a long time ago, this will be way easier. And so if I put in a 32nd, I get 2 times the 32nd is 2 32nds is 1/16. Minus 1 is, so negative. Negative. So I got negative and negative twice in a row. I want to go back to this and do the negative 1 in here. That would have been way easier. 2 times negative 1, negative minus negative, negative, positive, negative, and that's why. So we get overall negative. Okay, good. Now let's pick something to the right. So we'll go ahead and pick 1, right? That way this will be positive and positive. 2 times 1 is 2 minus 1 is overall positive. So we get a positive. So it looks like we do have a sign change there. Wow. This is tricky, but we're staying strong. So at this stage, right, we've determined where y is increasing or decreasing. But we still need our concavity. So let's go ahead and do y double prime. So let's go ahead and do y double prime. So our y double prime expression comes from the derivative of f prime. We've already seen that to be, as I import, 1.2 x to the 0.2 minus 0.6 x to the negative 0.8. Let's differentiate that expression to generate f double prime so we can perform our concavity analysis. So f double prime is given by power rule, and it looks like 0.2 times 1.2 is, what's that?
2.4.
Is it 0.24? 0.24? So 0.24 x to the, and now 1 less than 0.2 is what? Negative 0.8 again. Is that right? Minus exponent times the base times the constant. So I get negative 0.6 times negative 0.8 is overall positive 0.48. Are you guys getting positive 0.48? X to the 1 less than negative 0.8 is negative 1.8. Yes? I think we should do the same thing Evie was talking about before. Want to do that? Or, yeah, let's do the same thing. So what are we going to do now? Well, we're just concerned with the sign of y double prime. So we want to make this, if we can get this in fully factored form, it's going to be easiest to determine where my possible point of inflections are. So here we go. Let's factor out a 0.24 x to the negative 0.8. Yeah? That's going to be in each of those. So we want to do that. That would give me and remaining inside, we have 1 plus, and this looks like 0.24 times 2. And I need to get from 0.08 to negative 1.8. So is this again just over x? Because x to the negative 0.8 times x to the negative 1 is x to the negative 0.8 plus the negative 1 is negative 1.8. Is that right? So this would be times x over x. Also that we can do our possible points of inflection. So I'm getting x plus 2 all over x. Just so you know, I believe in you guys. Are there any values of x for which f double prime is undefined? Yeah, at 0, right? Because that's a 1 over x to the 4/5. So that x equals 0. And x equals 0. Are there any values of x for which y double prime equals 0? Yes, negative 2, and that's why, Evie, that was a great idea, because we can really concentrate on this when we do our science analysis. So we've got possible points of inflection or changes in curvature, PPIs, at x equals 0 and x equals negative 2. All right, let's do it. So we've got our y double prime number line. Labeling that, putting in our critical our possible points of inflection, I should say, at -2 and at 0. We'll do our sign analysis now, and we'll choose something to the left of -2, and I'm going to focus in on, this is a 4/5, and so this is always going to be positive, because of x, right? 1 over x to the 4/5, so x to the 4th on top is always going to be positive. So this is always going to be positive in front. And then, so we can just consider the signs here in this expression, right? We can just consider the signs here in this expression. So ready? I'm going to pick something to the left of -2. -3 should be okay, because we've already ascertained this is going to be a positive quantity. So if I did -3, I get negative over negative is positive. I'm going to pick -1 for this subinterval in the middle. We've already ascertained that this is going to be positive because it's 4/5 on the bottom, so x to the 4th is going to make that positive first quantity. Let's focus in on my binomial then. -1 in for x gives me -1 plus 2 is positive over -1 is negative, so that's overall negative. Stay strong, we're so close, you guys. At x equals 1, that's always going to be positive. I've got 1 plus 2 is positive, and positive is positive. Yes? Okay. So this was a challenge to generate our f prime expression or f double prime expression. But I'm excited now about our opportunity to put it all together and see if we can make a qualitative sketch. The last thing I want to do then is get our zeros. So what do I need? I need, what was our function? F of x. I'm going to just copy this quick. All right, so let's go ahead and get our zeros really quick to add that to the mix. So we've got zeros at if I set that equal to 0, I can get my zeros now help with our graph too. So when I set this equal to 0, I can solve by factoring. I can take out an x to the 0.2. And that would leave me with x to the first minus 3. So I must have zeros then. I must have zeros at x equals 0 and x equals 3. All my behavior happens in my changes of behavior, I should say, happens on the interval 0, 1/2. -2, 3, so I can get away with just going -4 to 4, and that should be everything. -4 to 4, because the 3 is our biggest thing. Let's go -4 to 4. So there we go. Okay, and our y-coordinates, we don't know, right? We don't know about any of our y-coordinates. If I plugged in 0 to my function, I get 0. And are there any other convenient things we could do, given that those are fifths? What is this function? X to the 6/5 minus 3x to the 1/5. Right, so are there any convenient values even to choose here? Only 30 seconds. 30 seconds, not so much. All right, well, I'm game if you are. So let's go ahead and make our graph the best we can. Ready? X equals 0, y equals 0, we've got a 0 here. X equals 3, y equals 0, we've got a 0 here. X equals -2, we've got a change in curvature from concave up to concave down. X equals 0, we've got a change in curvature, so I can put that. X x equals 0, we've got a vertical tangent because y prime was undefined, and decreasing before and decreasing after. So we can add that. And we've got a local minimum at x equals 1/2 because y prime changes from negative to positive. So a local min with a horizontal tangent because y prime equals 0 at x equals 1/2. So that's like here. And I need to change the curvature at x equals -2. At x equals -2, I need to change the curvature, but it has to be above that because I have a 0 there and we're decreasing. So changing curvature somewhere, I'll say here. All right. Concave up, decreasing, concave down, decreasing, vertical tangent, minimum at x equals 1/2, increasing 0 at x equals 3, and concave up after that. Okay, guys, going through decreasing concave up, decreasing concave down, vertical tangent, horizontal tangent, local min, 0. Oh gosh, concave up. That's the weirdest function I've ever seen in my life. In my life. Let's check. So thanks for sticking with me on this crazy foray into analytical calculus. We did that all without a graphing calculator, and now the moment of truth, we're going to see how our analysis stacks up to the numerical generation of the graph. And so let's go y equals, and we want to make sure we make a similar window so we can kind of see what's going on here. So we want a -4 to 4, and we want an original x to the, I don't know a good window for my y's, and so I'm going to just change it so we can get a good screenshot from that, Michael. I'm so sure. 1.2, close exponent, -3 x to the 0.2, close exponent, and window -4 to 4. And a y window. Do we have any point? 0, 0, 3, 0? I don't know. I'm going to go -6 to 6. Nope, -5 to 5. We'll see. All right. I don't know if this is a good window or not. There's no turn back, though. We're going for it. Uh-oh. Did you do something wrong? Oh, no. Oh, no. Vertical tangent. Minimum! You can tell I'm excited because it was touch and go there for a little while until Evie said, let's factor out the x to the 0.2. I was like, that's a good idea. Then we can just focus on our binomial factorization for the signs. Strong work. You get the go-to award today, Evie. That was go-to. All right, so how do we do? We did okay. I think that window's all right. And so I'm not going to mess with it, but I'm going to grab a screenshot so that we can PDF this bad boy. All right, what in the world is the second derivative test? Well, before we go any further, let's go ahead and look at when y prime was equal to 0. Were there any places where y prime was equal to 0? Yes. Y prime equals 0 at x equals 1/2. What is the sign of y double prime at x equals 1/2? Y double prime at x equals 1/2 was positive. What feature then must we have at x equals 1/2? We've got horizontal tangent, we've got concave up. Oh, that must be a local minimum, right? A local minimum? No? Yes! There was our local minimum. We got it. Okay, so that's the second derivative test. This time, it wasn't necessary because we had an expression, a symbolic expression for f prime. Awesome. That was tough, okay? That was tough. Now, should you run into something like this on your Unit 8 test, right? It probably won't be quite as difficult, but I wanted to make sure that we had some practice dealing with not your run-of-the-mill polynomial functions, because on the AP exam you'll have to deal with, those more challenging functions that we don't have an intuitive understanding, so people can't just use their pre-calc function behavior to make a picture. We want to be using the analysis with calculus in order to make a picture. That's the new learning, and that's why we have to grapple with some of these difficult ones. All right, we just have a couple to go, and then it's going to be our time for closing. So let's go ahead and take a look at a graphical application of the FTC revisited. And so we've already seen the relationship between a function and its derivative in terms of graphical behavior, increasing versus decreasing, and so on and so forth. We can now make a bridge between a function's derivative, right, and an area accumulator function, where we can kind of sum up my area between my function f prime and the x-axis to get corresponding changes in the y values of my original function f of x. Such is the case with example 3. So given the graph of f prime of x, let's sketch f of x on the interval -2 to 4 such that f of 0 equals 2. So we're going to go ahead and begin then. We only know one point. That sounds familiar. That sounds like an initial condition. We know that the point 0, 2 is on my graph of f. And so we're going to do f in blue. I only know one point on f right now, and that is 0, 2. So everybody, let's start with that. It's good that we have that initial condition. Now this harkens back to our unit 7, where we had a slope field, and based on that value of c for my constant integration, which represented a vertical translation on my original graph of f, I'd be falling in a different place on my slope fields, right? And I'd be following a different path to create my function. We need that initial condition so we know where to start. Now let's go ahead and scan my function f prime from the left to the right and add value or subtract value to my y coordinates based on area accumulated between the x-axis and f prime. In other words, I'm going to scan starting at x equals 0, right? Starting at x equals 0, I'm going to scan to the right, and I'm going to accumulate area. Any area in between f prime and the x-axis that's above is going to count as a positive contribution to my y values. They're going to increase when f prime is positive as I scan along from left to right. My y coordinates on f are going to decrease when f prime is negative as I scan along from left to right. So we're trying to make a connection in multiple ways between a function f and its derivative f prime. Let's go ahead and scooch along the function from left to right. And so here we go. As we move from x equals 0 to x equals 1, was f prime positive or negative? I like scooch. Scooch is fun. I'm not quite sure how to spell it, right? But at least we got it on the recording. So as I scan from left to right, between x equals 0 and x equals 1, is f prime positive or negative? F prime is positive. Would I expect my y values on f to increase or decrease on this interval? I'd expect them to increase. By how much? I'm going to have to guess. It looks like that's about 1/3 of a unit. So I'm going to go up 1/3 of a unit to about here. What feature occurs on f when f prime equals 0? That is, when f prime has an x-intercept, what does f have?
Local max.
It has a horizontal tangent. In this case, it is a local max because f prime switched from positive to negative. So here we've got a horizontal tangent. Now I'll continue scanning as I go from x equals 1 to x equals 2. It looks like I lose about 1/3 of a unit. As I continue scanning from x equals 2 to x equals 3, it looks like I lose a little bit more than 1/3 of a unit. Yes? And now, as f prime switches from negative to positive, that indicates the presence of a local minimum on f. How come? Because f must change from decreasing to increasing when f prime switches from negative to positive. So this must be a local minimum. Horizontal tangent, local maximum. Continue scanning from x equals 3 to 4. It looks like I add on another 1 and a little bit more units, so I'm going to go a little bit higher. I'm going to go about here. Yes? Let's go backwards. I'm scanning backwards now. From x equals 0, I'm scanning to x equals -1. it looks to me like that's a little bit more than 1/3 of a unit. It's above the x-axis, but I'm scanning now from right to left. So that positive contribution when f prime is above the x-axis now is going to be a negative contribution. It's going to be the opposite as we move backwards. Yes, because we're scanning from right to left. So should my function value from y equals 2 go up or down? It should go down. So let's go ahead and go down about that much. Still scanning. That looks like 1 plus a little bit more. Yes? All right, let's do it. So we had what feature here? Oh wait, no, that's going to go up. That'll go up. A little bit more than 1. How's that? Horizontal tangent here. Mighty call, good catch. Can we do it? Can we do it? We can. So it looks like dang, Craig. If we wanted to even get a little bit crazy, we could say point of inflection when, get this, f prime has a local max or local min. That is when f prime switches from increasing to decreasing, y double prime would switch from positive to negative, indicating a change in curvature on my original line. So if we wanted to get crazy, we could say that right about here we have a point of inflection, and right about here we have a point of inflection on my original y. Awesome. Pretty impressive, guys. Pretty impressive. Okay, so we totally did that, and we totally did that, and we did that. All right, the last thing we're going to start, and this will be included as part of your OTL, if we're given an original graph, we can tell all kinds of things about f prime or f double prime. We just need to make sure that we're on the right rung of our ladder. So as we consider this picture number 1, in number 1, we're given a picture of y equals f. And so we can tell all kinds of things about f prime and f double prime based on our original picture. It appears that f prime, right, f prime is positive whenever f is doing what? Well, whenever f is increasing. And so as I look at this, I can get my value of x for which f prime is positive by looking to see when f is positive. So I would state interval notation. This is supposed to be from x sub 2 up until x sub 4, union x sub 7 up until x sub 8. We'll skip all the way down to, we can do those. How about f prime equals 0? When does f prime equal 0? Oh, when f has a horizontal tangent. And so f prime equals 0, we'll do C, would be when x sub 4 and anywhere else? X sub 7. That's not interval notation. There's no parentheses. I'm going to make this and. All the rest you can do easy cheesy. Let's do a double prime. F double prime is negative when f is concave down. So respecting my original graph of f, it looks like we're concave down on x equals 0 to x equals, I'm sorry, x sub 0 to x sub 2. Then we're going to parentheses it because we've got this cusp here. But we'll pick right up with it because we don't change curvature. We'll go ahead and say x sub 2 then to what? X sub 5. So we'll go ahead and do G together. X sub 0 till x sub 2 union x sub 2 till x sub 5. That's good enough for now. Let's do 1f prime. Look at it, guys, you're going to complete this as part of your assignment. I just want you to look at number 2 now. So if y equals f prime of x, right? If y equals f prime of x, now we have to determine what ladder we're on. So f is increasing when f prime is what? Positive. And so for this, we're looking at f prime. We're looking at f prime. So f is increasing when f prime is positive. In this case, that's x sub 1 up until x sub 3. You guys see? So we have to be knowing what ladder, what rung of the ladder we're on. In this case, we're looking at f prime. So f double prime, we'll do number 3, is positive when what's true about f prime? When it's increasing. And so in this case, now we're x sub 0 to x sub 2. So these are going to be great practice, okay? These are going to be great practice, but that's all we're doing. Okay, let's close it up then. You guys did great work today. We need to state the second derivative test in 4 minutes. Answer the question, is the relative maximum value an x-coordinate or a y-coordinate? Is the global minimum value an x-coordinate or a y-coordinate? And lastly, must one construct a y prime number line to determine the absolute extrema on an interval? Okay, so a written response for each of these. I'll give you about 2 minutes for that, and then I'll close it up in the last one, and it'll be perfect time. Okay, ladies and gentlemen, let's go ahead and close it up in the interest of time. So let's state the second derivative test. Riley Freeman.
If y prime is equal to 0, y double prime is greater than 0, then y is equal to 1. And if y prime is equal to 0 and y double prime is less than 0, then y has a 1.
Awesome. So we've got y prime is equal to 0, y has a horizontal tangent, and the sign of y double prime then will determine whether or not y has local max versus local min. So it looks like y double prime equals 0, and y prime positive means we're dealing with the local minimum. Y prime equals 0, y double prime negative means that we're dealing with y having a local maximum. Raise your hand if you got the same as Riley. Got the second derivative test, great job. Is relative maximum an x-coordinate or y-coordinate? Is global minimum value an x-coordinate or y-coordinate? Emily? Absolutely. So maximum is a y-coordinate, the minimum is a y-coordinate, and so the minimum and maximum values of a function are y values. Good job. Thank you. And lastly, must one construct a y prime number line in order to determine absolute extrema? Grace?
No, you can just compare the y values like a calculator.
Good. We'll just compare the y values of the critical points with the y values of the endpoints and select the absolutes. Good job, you guys. That was a serious day, but good work. An important day. I'm going to stop the recording and post it to Moodle.